So we're going to start with an organism that's embedded in some environment. We're going to call these like environmental states with this symbol here, new. So the environment might have like different environmental states, and the way that the organism perceives it is through sensory states. So the organism can only observe these sensory states, not what's out there in the world. For any given sensory state, like let's say that the organism is observing sensory state 7, it might have been caused by any one of these three. It can't tell for sure. So it's in this situation where it's observing one sensory variable and it's trying to guess which one of them caused it. Of course, like they're not all equally likely, and so the organism is trying to put a probability distribution on these environmental variables given the sensory variables that it observed. This is the goal of the organism. So the correct way to do this is via Bayes' rule. However, this integral here for most interesting cases is going to be intractable, and so organisms are not going to be able to use Bayes' rule typically for computing this posterior. Another way to do this, which is more tractable, is to come up with a simple distribution that's computationally efficient to work with, and try to minimize a distance measure between this and the posterior. Now this sounds crazy given that we don't know what the posterior is, but we're going to change this problem into a simpler, like an approximation of it, or at least show that it's equivalent to minimizing a different distance measure that we can compute within the brain. And we're going to be able to complete this task. So how do we do this? Let's write down what we want to do. What we want to do at the moment is to minimize a distance measure between these, and typically we're going to be looking at the KL divergence, the Kullback-Leibler divergence between Q and the probability of nu given phi. And notice that if we do this, then really like we've achieved what we want to achieve, because Q is going to give us the answer that we want, which is the probability of nu given phi. And it turns out that this measure can be broken down into this plus the log probability of phi. And this is the KL divergence between Q of nu, which we're coming up with, which we're calling the recognition density in the context of the free energy framework. And this joint distribution of nu and the sensory states phi is known as the generative density, because it relates how phi is generated by nu and the probability of nu itself. So we can write this down. And this KL divergence, this new KL divergence that we're writing down, is the free energy F. We're going to denote this as F, plus this log probability of phi. Notice that this KL divergence has a minimum, it must be greater than or equal to 0. So we know that the free energy F that we've written down here, this KL divergence, plus log probability of phi, must be greater than or equal to 0. And so one nice thing about the free energy, which we're hopefully able to compute, or at least approximate, is that it gives us an upper bound on the surprisal of the sensory input, which is a nice property of it. So another nice thing about writing it down like this is that we notice that minimizing this KL divergence here is the same as minimizing just this KL divergence with respect to Q. So remember, like here what we're doing is we're picking Q that would minimize the KL divergence, and regardless of what Q we pick, this quantity here is not going to change. And so the message here is that we are picking Q to minimize this KL divergence, and that's going to be the same Q that will minimize this KL divergence, which is a nice thing because we're supposed to have access to this expression, or at least we can approximate it, as we'll see now. So let's turn our attention to this particular KL divergence here. So let's again write down what we want to do. We want to pick the Q of nu that will minimize this other KL divergent measure between the R density and the G density, where the R density is Q of nu and the G density is this joint. This is what we would like to do. And at this point, we should figure out what distribution we want to use for Q, and there are several candidate distributions. One of these is the normal distribution. So we're going to pick Q of nu, or actually we're going to pick nu to be normally distributed with a mean of mu and a variance of zeta. This is what we're going to pick. We're going to say that nu is going to be normally distributed with a mean of mu and a variance of zeta. And we're going to write down this expression and see where that can take us. So the KL of Q and this is going to be, by definition, the integral over mu of the following. And we can expand this by writing Q log Q minus integral of Q log this. And here I used the identities log A over B is equal log A minus log B. And if you have x plus y, you can write this as the integral of x plus the integral of y. So these are the two identities I used to do this. And next, we're going to plug in, for one of these Q's, the definition for the normal distribution. So if you have a normally distributed variable, its distribution, known as the probability density function, is the following. 2 pi variance times the E, Euler's number, minus this is just the probability density function of a normally distributed variable. You can grab this expression from Wikipedia. And so we're going to plug this here with where the log is. So it's going to be Q log of this expression here. So it's Q log of this expression minus the integral of Q log the joint, which we haven't touched yet. So next I'm going to expand this log into the function. Actually, let's give ourselves a little bit more space. So this can be written as Q log 1 over 2 pi zeta plus the log of the exponential of 2 zeta. Cool. And now we can expand Q into each of these and expand the integral as well. And so we're gonna turn this thing into two different integrals just by expanding. So it's going to look like this: 1 over 2 pi zeta d nu plus the integral Q of nu into log of x of this. But note that log of x, like if you have log of E of x, that's just x. And so these kind of cancel out, so we can just write in the expression that's in here. So let's do that. Over 2 zeta d nu minus just the same expression up here. So notice that this here does not depend on Q of nu, and so we can take it out of the integral. So what we'll have is, oh, I forgot the square root here. So 1 over the square root of 2 pi zeta into the integral of Q nu d nu plus the integral, and we can do the same thing here. We can take the terms out that don't depend on nu, and that's the minus and the over 2 zeta. So we can take that out. We can say minus 1 over 2 zeta into the integral of Q nu minus mu squared minus this thing here. Notice that the integral of Q nu d nu, we're integrating over all of nu of a probability function, and that by definition is 1 for all probability distributions that are valid. So you have any probability distribution, probability density defined over x, then the integral of p of x dx is 1 if it's a proper probability distribution. And so what we can do is just replace this by 1. And so it's log of this times 1, so it's just going to be the log of this. And let's also simplify this. So we can write this as 2 pi zeta to the power minus 1/2. And then we can take the minus 1/2 out here, which is a nice property of logarithms. So we can write minus log of that over 2. Minus 1 over 2 zeta. And now we notice something else here. This integral, the variance of x, is defined as the integral of x minus the mean of x squared times p of x dx. This is the definition for the variance. And so here by pattern matching, you can see that you have like p of x here, you can like pattern match this, times x minus the mean of, so here mu is the mean of nu, so this is mean of x squared dx. And we're integrating over all of nu here, and here we're integrating over all of x. And so just like this is the variance of x, this is going to be the variance of nu. And so we can write now that this whole integral here is going to be the variance of nu, which we've already defined to be zeta. So we can replace this whole integral by just zeta. So let's do that. We're just going to here multiply by zeta minus the integral of q log p of this. And so now we've reached the situation where the free energy, which we want to minimize, is written as follows. 2 pi zeta minus 1 over 2, because these just cancel out, minus the integral of q log p nu phi d nu. So can we simplify this further? What we're going to do is we're going to try to get rid of the dependence of this expression on this probability value here. So we're going to define the Laplace encoded energy as a new function, the negative log of probability of nu and phi. And we're going to try to approximate this to get rid of nu. And one way to do that is to use a Taylor expansion about nu equal mu. And we're going to build, essentially, like what this does is that we're going to try to build a polynomial that approximates E around the region mu. So, for example, like if you had a cosine function, just to explain like what the Taylor expansions are, if you had a cosine function where on the x-axis you have x, on the y-axis you have cosine of x, and it looks something like this, let's say, then suppose you wanted to approximate cosine of x around this point with a polynomial, with like a second degree polynomial. What you would get is something that looks like this, which is a good approximation of cosine x around this point, like around the point that you want to approximate at, but it's a very bad approximation of cosine x around, let's say, this point here. And so this will work if most of your function, if like the function of interest is only like tightly concentrated at that point. And you can do this like at any arbitrary point. So if you pick this point, you can also like build another polynomial that would approximate this. So in our case, we have this function e that we're trying to approximate, and we're going to do that with a second order polynomial. And there's essentially a way to do this. You're going to take derivatives, the nth derivative of that function, whatever the function is. In our case, it's going to be the function e. So we're going to take the nth derivative of e, evaluated at mu, and we're going to multiply that by nu minus mu to the power of n divided by n factorial. So this is how you, this is what a Taylor expansion means. This is how you build the polynomial, if you wanted to do it to the second degree. Of course, like Taylor series are much more general than this. You can go up to infinity if you want to approximate the function better and better and better. But here we're going to limit ourselves to a second degree polynomial. And so what will that look like? What we're going to get is essentially e of nu and phi multiplied by nu minus mu to the power 0 over 0 factorial plus the derivative of e with respect to nu multiplied by nu minus mu over 1 factorial, this is to the power 1, plus the derivative of e, second derivative of e. And here we're evaluating its derivative at mu. So, like for example, if you're evaluating the derivative of cosine x at the value pi, you would get minus sine of x, but you're evaluating it at pi, and so you get minus sine of pi. That's what it means to evaluate the derivative at a point. And here we're taking the second derivative with respect to nu, also evaluated at mu, multiplied by this squared over 2 factorial. So here, this will just cancel out, this will cancel out, these are 1. Like anything raised to the power 0 is 1, 0 factorial is 1, 1 factorial is 1, nu minus mu will stay where it is, 2 factorial is just 2, and so we can continue writing this. It will look like this. Plus the derivative, well, the first derivative of e, we're just shorthand going to write it this way, into nu minus mu, plus half of this second derivative of e with respect to nu, evaluated at mu, times nu minus mu squared. So this is what we're going to approximate. We're going to approximate e. Let me get rid of this stuff to make some more space. So we're approximating e nu phi like this. And so now we can go back to our original expression, which was, it included this e term. So so this will turn into a plus, and we're going to write here e of nu and phi d nu. And now instead of e, we're going to plug in the approximation that we just computed. And that approximation is this one right here. Alright, so now we can write f as the following expression. Negative half log 2 pi zeta minus half plus the integral of q nu multiplied by this approximation. So this is more correctly an approximation of f, because we're approximating e. And the approximation of e was this Taylor expansion. And so now we're going to expand this to see if anything simplifies. So we're going to expand q into this expression here. So we're going to get e nu phi d nu plus integral of q into nu minus mu into dE d nu evaluated at mu plus the integral of q d nu here plus the integral of q into the second derivative evaluated at mu into this squared d nu. So this is the expression we get. Notice that we can take this out, and what we'll be left with for this part of the equation, we're just going to look at this term here. It's going to be the integral of q nu into nu minus mu d nu, and we've taken out the derivative term. Now notice that this here must evaluate to 0, because this is the expected value of nu minus the expected value of nu. And so this is the expectation of nu minus the expectation of the expectation of nu, which is just 0. Because an expectation of an expectation is just the same thing, and this is 0. And so this integral evaluates to 0. We don't need to worry about this term at all, so we can not focus at it anymore. So we can write this down as this integral here, q nu minus mu squared d nu. So now notice that this integral right here is the expected value of nu minus its expected value all squared, which is the definition of the variance of nu. So this is just zeta. So we can rewrite that as just zeta. So our free energy now is approximated as the following quantity. Alright, so now what we have is that f is a function of zeta, mu, and phi. It doesn't depend on the other variables anymore. And this is a nice step forward, because now we have f is a function of some variables that we can optimize with respect to. So we're going to change these parameters here. We're going to look at different ways to change these parameters in order to minimize the free energy. And actually what we're going to focus on is how to change mu to minimize the free energy. That's what we're calling inference. Or we can try to change the sensory data to lower free energy, which is known as active inference. Well, there's some nuance there, but that's the basic idea. So let's summarize what we have so far. We started with an organism that is trying to get a probability distribution over the states in the environment given its sensory input. And the way we're going to do that within the free energy framework is to define a different probability distribution Q, and we're going to try to minimize some measure of the KL divergence here, so that these two are close together, so that Q gives us a good approximation for this posterior that we're interested in. And it turns out that minimizing this KL divergence right here is the same as minimizing a different KL divergence between Q and this joint, which we've called the free energy. So minimizing this KL divergence is the same as minimizing the free energy. And then what we did was we made some assumptions on Q, and we made some other approximations like this particular expression. We approximated it with Taylor expansion, and by making these assumptions we were able to arrive at an expression for the free energy that we can optimize. So this is an optimizable free energy, optimizable via gradient descent. This is what we've done so far. And so for the rest of this video, what we're going to be showing is that we can do perceptual inference by optimizing this f optimizable by gradient descent relative to, depending on what we're doing. So if we're doing perceptual inference, we're going to optimize with relative to mu by gradient descent, whereas if we're doing active inference, we're going to also take the gradient of f, the optimizable f, but instead we're going to take the gradient with respect to some action. But the basic idea is the same. The idea is that we're going to figure out how to change mu over time. So we're going to say that the mu at time t plus 1 is equal to mu at time t plus some difference here. And we're going to iteratively make these steps such that this will minimize, like this will be in the negative direction of the gradient. And the same thing for action. We're going to, like when we're doing active inference, we're going to choose actions that will minimize action here. We're going to choose these differences at each time step that will walk us down the function f. And by doing this, what we've done is essentially lower this original KL divergence. This is the idea. So we're going to optimize f to lower the KL divergence between Q and the true posterior that we're trying to minimize. This is the whole story of the free energy principle. The rest is going to be just like mathematical detail. We can still simplify this even further by making some assumptions. For example, we can fix zeta here to a constant value, and that value will be the one that will minimize the free energy. So we're going to pick the zeta that will set the derivative of f with respect to zeta to 0. So we're just going to take the derivative of the above expression and set it to 0, solve for zeta. So this is what that looks like. Taking the derivative with respect to zeta. So here I've just expanded this term. And now I'm going to take the e term here doesn't depend on nu, so we can take it out of this nu integral. And so this is our expression. So we're going to expand the derivative into this expression. We'll find that the derivative with respect to this is 0 because it doesn't depend on zeta at all. So this goes away. The derivative of this is also 0 because zeta doesn't appear there. And notice that this is actually equal to 1. So we can stop considering this as part of the expression in the first place. So we can go back to this original expression and actually erase this. And finally, this term will depend on zeta, the very last one here. So we leave it alone. So what we're going to get is... So this is the expression that we're left with. And now we actually want to take the derivatives with respect to these. The derivative of log x with respect to x is 1 over x. So we'll use this rule here for log zeta. So what we'll get is 1 over zeta. And here we can call this zeta star because it is the zeta that will minimize f. So it's a special constant zeta. Plus the derivative of this term here relative to zeta is just going to be this term here, because the derivative of ax relative to x, if a is a constant, is just going to be a. So now we just want to solve for zeta star, and the rest is just a little bit of algebra, and we'll find that zeta star is equal to the inverse, or the reciprocal. It's equal to 1 over this. So we found zeta star. And now we can go back to the original expression and plug that in. So the original expression is right here. So here we'd like to plug this zeta star in instead of zeta to make this assumption. So this optimizable f is now half log 2 pi zeta star. We can leave this one just like that. And now notice that if we're going to be plugging in zeta star for this zeta here, it's going to cancel it because it is equal to its reciprocal. So these cancel out, and then what you're left with is plus half minus half here, so these also cancel out, and you get a nice little expression with just 2 terms. And the nice thing about zeta star is that it depends entirely on this expression here. It's kind of pegged to it, and so if we want to pick the mu that will minimize the free energy here, it's not going to depend on zeta at all. And so minimizing f is going to be equivalent to minimizing e. So our problem becomes a little bit simpler. It becomes the problem of finding the mu that will minimize this Laplace encoded energy. And to remind you what this is, this was defined as the negative log probability of mu and phi. So now we can write down this expression that we want to minimize. We want to minimize this. We want to choose the mu that will minimize this. And so what we're going to do is we're going to break this down into its components times probability of mu, where this is the likelihood of the sensory data given a particular mu, and this is the distribution over all possible the brain states mu that are generating phi. So here there's some generative process by which phi comes about. It comes through essentially a function of mu plus some noise, where if you pick a particular mu, g of mu is supposed to be a constant. And so you're adding a constant to this noise term, where the noise is a random variable. And the noise is going to be a Gaussian with mean 0, and variance we're just going to choose like sigma z. We're going to call the variance sigma z. And because we're adding a constant to it, we're interested in what phi is distributed as. Phi is going to be distributed as the mean plus whatever the constant was, which is g of mu, and the variance will stay the same since we're only adding a constant. So now we have a distribution for phi given mu, which is this, and we can write this down in the form of a PDF. We're also going to assume that mu itself is normally distributed, and it's going to have a mean of mu bar and a variance of sigma w. So we're going to assume that mu is generated via the following process. It has some mean value and some noise w that's Gaussian and centered around 0. So now we can write down the expression we want to minimize. It's going to be minus log of the PDF of phi given mu, which is the PDF of this. So all of this is just probability of phi given mu times the probability of mu, which is also going to be a Gaussian with a different variance term. And essentially this is the expression that we want to minimize. So we want to pick the mu that will minimize this expression. So here I've just colored them differently. And so we're going to expand this expression by taking the log of the reds plus the log of the exponents. So here I've expanded the logs into essentially this value here times this value here, which lead to this term inside the log. And I've also multiplied the two exponents, which led to the expression in here. And remember, if you have like ex times ey, what you'll get is ex plus y. And that's why I've summed the terms that are here and here. Also note that log of an exponent of x, like log e to the power x, is just x. And so the log and the x here cancel out. So what we're left with, this expression here, e, is the log of this constant term here, which I've just taken the power outside, which you can do with logs. So if you have like log x to the power a, it's equal to a log x. That's the rule I used to change the red one to this one. Minus this term here, which I've only cancelled the log and the x. And so here we can change this in its place to put a plus here and a plus here. And this is the expression we're ending up with. So e is a function of these three entities. Now notice that this value here can be conceptualized as a prediction error, and so can this value here. So we're going to call this one the sensory prediction error, because we're getting some sense data here, and we're going to conceptualize mu as a prediction of what the data is. So this is a sensory prediction error, and we're going to conceptualize this as a model prediction error, because the model had some kind of expectation of what mu should be, and this is what this is the mu that was observed, or this is the mu at that time point. And so in this framework, these are going to be labeled as epsilon like this, epsilon z, and epsilon w for the model prediction error. But for now, we won't worry about these. Our interest now is to find the gradient of e with respect to mu. We'd like to change mu so that e is minimized, and so we are going to look at the gradient of e. And so to do that, we'll take the derivative with respect to mu of the whole expression up here. So it looks like this, and the derivative with respect to the first term is going to be 0, because there's no mu in here, so this goes away. Now let's look at the derivatives for each of these separately. For this term here, the derivative is going to look like this, just via the chain rule. So these cancel out, and you get this expression, plus the derivative. Now I'm going to take the derivative of this, and it's just that. And so we found an expression for the derivative of e with respect to mu. And so if you change mu along the negative direction of this derivative, you have a process by which you can update mu to yield lower and lower energy with each time step. So we're going to set this thing here to the following. where we've worked out an expression for the gradient of E. And so this presents a process theory by which we can update mu via the dynamics of the neurons that depend on prediction errors. So this is a prediction error, this is a prediction error, and only locally available information in order to get you a mu that's closer and closer to the sensory data. So just in the spirit of completing this example here, we're going to make some assumptions on g of mu. So remember that phi was distributed as a normal distribution with a mean of g of mu and a variance of sigma z. And now we're going to assume that g of mu is just mu, just to work out an expression for this gradient descent formalism. And so if we want to write the full gradient descent, it just looks like this. Okay, here's a learning rate. Plug in this sensory prediction error, and actually it's not squared. It's not supposed to be squared. So this is going to be the expression. And if we expand this out a little bit more, we get the same expression as in predictive coding. We're going to have the following. So this expression above simplifies to the expression below, and so you're having prediction errors that are going to be weighted by the variance here. And so this is the idea of precision-weighted prediction errors that are being used to update the brain states.